Iceberg charts. You know them, they got the popular information at the top and the more obscure and unknown information at the bottom. Today, I'll be showing you an iceberg chart about the universe. Pretty big topic, I know, so let's get started. If you live on Earth and you're a human, chances are you've probably heard of or even seen a star. If you haven't, stars are basically huge balls of plasma constantly undergoing fusion, which creates a ton of energy and light and radiation. The planet you're most likely on, the Earth, is actually orbiting around a star that we call the Sun, which technically doesn't look like this. Yeah, NASA, we get it. The Sun isn't technically orange and yellow. Now, can you please shut the fuck? Once you put enough of these stars together, you get Galaxies are basically groups of stars and some other stuff, which in most cases are orbiting around a supermassive black hole, we think. They're pretty big, there isn't much more to say, you probably already know all this, so let's just move on. Now, chances are, if you went to school, you probably have at least heard about the Big Bang. The Big Bang is a theory that the universe stems from a tiny little speck of super high pressure matter, which immediately expanded into what we call the universe, and I'll talk more about this later. Gravity is a natural phenomenon that brings everything, matter and energy, together. If you are a thing in the universe, you have likely experienced this natural phenomenon before. In fact, you're probably experiencing it right now. Fun fact, you are not only being attracted by Earth, but you're also attracting Earth to you, since all matter has gravitational pull. The speed of light is a physical constant of 300 million meters a second. The speed, it's actually 299,792,458 meters a second. Right, anyway, the speed of light is, according to special relativity, the highest speed that matter, energy and information can travel. This means that no matter how hard you try, with our current understanding of physics, you cannot go faster than this. Because information travels at the speed of light and the universe has only been around for about 13.8 billion years, this means that there are parts of the universe that are so far that it would take light longer than the universe has existed to reach us. This spherical region that has had time to reach us is called the observable universe. Remember that Big Bang thing I talked about earlier? Turns out it's not actually an explosion, it's more like the expansion of the entire universe itself. When we think about the Big Bang, we often think about a big bang. Matter condensed to a tiny little state and then exploding out into the universe. But actually, the Big Bang was the entire universe itself, and it was the universe that expanded enormously, causing the Big Bang. The universe is still expanding to this day, but it's not an expansion in the sense that the universe is increasing in size with the middle, no. That would be way too simple and convenient. Instead, look at it like this. Imagine a balloon with points drawn onto it. Now imagine that you are a two-dimensional being on this balloon. When looking at these points, you would see every point expand away from each other. Oh, and did I mention that the universe expands faster than the speed of light? Atoms are the smallest unit of matter. In case you weren't aware, every physical thing in your daily life is made of atoms. All atoms have a nucleus and some electrons orbiting around it. The nucleus itself is made of protons and neutrons, and by changing the nucleus you can get different atoms. If you combine these atoms, you can get different molecules and chemical compounds. The word atom originally means indivisible particle, but as it turns out, that is not the case. Subatomic particles are particles even smaller than the atoms. The neutrons and protons we talked about are subatomic particles, but the neutrons and protons themselves are actually made of quarks. There are 6 total flavors. Yes, they're called flavors of quarks, but there are also some leptons, gauge bosons, and Higgs bosons. Anyway, they're small, that's all you gotta remember. Let's zoom out a little from the subatomic particles and, oh no, we zoomed out too fast and accidentally created a black hole. But what even is a black hole? Well, a black hole is a small little region of space that weighs so much and is so dense that gravity is so strong that nothing can escape from it. Now I know what you're thinking. Yeah, that's fine, but what is it? Is it a hole? Is it just a really dense sphere of stuff? Well, according to general relativity, we have what is called a gravitational singularity. Imagine not a black sphere of matter, but a point, a single dot in space that has infinite mass and gravitational field. You might say, well, that defies the laws of normal space-time. And yeah, you're right, it does. When you look at a black hole, you actually see the event horizon, which is the area where light cannot escape, not the black hole itself. Also, if you jump into a black hole, you will get stretched out. This is, and I'm not even kidding, called spaghettification. But how does a black hole appear? Well, once stars spin out, the energy of the fusion it was creating is no longer keeping it from imploding, and the star implodes into one of three stellar remnants: a white dwarf, a black hole, or a neutron star. If the star that imploded has about 20 to 25 solar masses, it becomes a neutron star. Excluding black holes, they are the densest stellar object we know of. Neutron stars have incredible properties, the craziest of which is the fact that the inner crust of a neutron star is called nuclear pasta. You probably already know about the planets of the inner and outer solar system, but it may surprise you to hear that there are actually a ton of other objects in our solar system. Objects that are further than Neptune are called Trans-Neptunian objects. The most popular of these is the exoplanet Pluto, but there is also the dwarf planets Iris, which is more massive than Pluto, Haumea, which is formed like a potato, and Makemake, which has an average temperature of 40 Kelvin. And the last two were discovered in 2004 and 2005. The theory of relativity is a theory that you have likely heard about before. The theory of relativity is comprised of the special relativity theory and the general relativity theory. Let's start with special relativity. Special relativity is based on two postulates. 1. All of physics are identical for all frames of reference if they are in constant speed. Imagine you're on a train. When the train starts, you can feel that you're pushed back into your seat, but once the train is at a constant speed, you're not really being pushed around. What you feel is not the speed of the train, but instead the acceleration of the train. Right now, you're on the surface of the Earth. At the equator of the Earth's rotation is about 1,670 kilometers per hour. But because the speed of the Earth's rotation isn't changing, we don't feel it. 2. The speed of light in vacuum is identical for all observers regardless of how the source is moving. Explaining this postulate is long and complicated. Basically, the speed of light is a constant, and this was revolutionary at the time. Here's a full explanation. If you're interested, you can pause the video and read it. Oh, and by the way, this violates Newtonian physics, because why not? The second theory of relativity is the general relativity theory. The general relativity describes gravity and is our current interpretation of gravity in modern physics. The general relativity theory essentially states that space-time curves when there is matter, energy, and momentum, creating gravity. So apparently, scientists were looking around in space and were like, it looks like there should be around 5 times more matter here, otherwise the galaxy would just fly apart. Maybe there's actually matter but we can't see it. What are you trying to say? Maybe this matter we can't see is in a way dark, so we can't see the matter. You know, what the hell are you talking about? So a new theory was born. Dark matter is thought to account for about 85% of all matter in the universe, and is more of a theoretical type of matter rather than an actual one we've discovered. If it does exist, it is a form of matter that pretty much only interacts with radiation and other matter through gravity, making it fairly exceptional and unexplainable. Dark matter is not to be confused with the theory of dark energy. Similar to the theory of dark matter, seeks to give an explanation to the missing energy in the universe. Dark energy is said to contribute to 69% of all energy in the observable universe. And unlike dark matter, we have observed evidence of its existence from measurements of supernova. You've probably already heard of antimatter before. It's often mentioned in science fiction, but what is it? Well, antimatter is matter composed of antiparticles. I'm kidding, I know this isn't very descriptive. Look at it like this. Every particle has an antiparticle with the exact same mass, but with the opposite charge. But what does it have to do with antimatter? Well, as I said earlier, antimatter is matter made exclusively out of these antiparticles. But here's the cool stuff. When a particle comes in contact with this antiparticle, a ton of energy is released. This explosion is remarkable because the amount of energy released proportional to its mass is the highest amount we have ever observed. To understand why it's remarkable, you must first understand E equals mc squared. You've likely seen this equation before, and it basically states that all mass equals an amount of energy. This means that, in theory, 1 kilogram will always be equal to an amount of energy, regardless of where that mass comes from. This means that 1 kilogram of dirt and 1 kilogram of enriched uranium is equal to, on paper, the exact same amount of energy. The only reason why enriched uranium is what we're using to power our light bulbs is because it has certain properties that makes it easier to do so, but that's it. That is, in this context, the only thing that separates the two. The big challenge when it comes to generating electricity is that it is hard to extract energy out of matter. We typically end up with very small amounts of energy compared to the amount of mass we put in. Let's take coal for example. 1 kilogram of coal gives back the equivalent of this much kilograms of energy, which means that about this percent of its mass gets converted into energy. That's a lot of zeros. Uranium has an efficiency of 0.1%, which although much higher is still not much mass getting converted into energy. This is where antimatter is interesting, because it has an efficiency of 100%. But unfortunately it currently requires way more energy to make antimatter than you get out of it. Wormholes are a theoretical structure or hole which connects different points in space. When we think of the universe, we often think of some flat plane or some three-dimensional cubical box, but that might not be the case. If the wormhole theory is correct, a wormhole would be able to bend space-time in the 4th dimension. But since it can be pretty hard to imagine a 4-dimensional universe, let's imagine that the universe as we perceive it is 2-dimensional instead of 3-dimensional. Let's say that we have 2 points and we want to travel from here to here. But that's a pretty far trip. Luckily, scientists in this universe have been able to create a wormhole, and in this theoretical example, the wormholes would essentially bend the universe into the 3rd dimension, like so, connecting 2 points. From our perspective, since we see the universe in 2 dimensions, it would look like a tube has appeared, basically transporting us to the other side of the universe. If you add one more dimension, you have a simplified version of the wormhole theory. Cosmological epochs are a way to divide the history of the universe into different epochs. As we talked about earlier, the universe began with a Big Bang. Here begins the first epoch. In the beginning we had the very early universe, which itself is comprised of 6 epochs. The very early universe was very weird and the fundamental forces of the universe were combined together. At this point, we're in the early universe. The universe is full of super hot quark plasma, and the quarks turn into protons and neutrons. After approximately 2 minutes, nuclear fusion starts to occur and protons and neutrons are making new atoms. Then, not much. After about 100,000 years, the temperature finally allowed for some of the first molecules to be formed, and for the next 200 to 300 million years, the universe would be in what we call the Dark Ages. Right until the first stars started to appear, which meant the creation of a ton of new different molecules. After about 700 million years, the first galaxies started to pop up, and among these were ours, the Milky Way. About 9.2 billion years after the Big Bang, our sun was born, and the rest is history. What a story, huh? But what happened before and after the Big Bang? Well, the truth is, no one knows what happened before the Big Bang, and we can only guess what will happen in the very distant future. There are lots of different guesses as to what could happen. Let's go through them. The first is that the expansion of the universe will eventually reverse. This theory is called the Big Crunch, and it essentially states that our universe will contract all the way back and the Big Bang will repeat. A more specific version of the Big Crunch is the Big Bounce theory, which says that this sequence will repeat indefinitely. The second, more widely accepted theory of the universe is that the universe won't start contracting. This can either mean one or two things. One, the universe will keep expanding at an ever-increasing rate like it does right now, and eventually events like the Big Rip will occur where the universe will have expanded so much that all matter down to the quantum scale will be ripped apart. Also, the Big Freeze, where the expansion of the universe will gradually slow down until all energy in the universe will be evenly distributed. Motion and activity generally means that energy is being transferred from one object to another, but since all energy is evenly distributed, nothing can happen, and the universe will just be particles floating in space. This theory is also known as the universe heat death. Let's say we have 2 objects, and they have a total energy of 10 energy units. Now, let's say that the energy units are distributed randomly between them. If each energy unit has a 50% chance of being in either one of the objects, then odds are they will probably be somewhat evenly distributed. In other words, the chance of one object having all the energy is low. The larger the objects are and the higher the amount of energy is, the more likely they are to be evenly distributed. If you have a mug of coffee and some ice next to it, then through simple probability the energy will move towards an even distribution. This force is in reality just a result of randomness and probability and has a large impact on our universe. Pulsars are stars, typically neutron stars, that emit radiation from their magnetic poles. Pulsars form when the core of the star is about to be collapsed into a neutron star. The star's angular momentum is retained by the forming neutron star, but since the neutron star is way smaller, it has an enormously high rotation speed. How fast does it rotate? Well, let's have a look. The fastest spinning pulsar is PSR J174824446AD. It rotates 716 times per second. Because pulsars, think about that for a second. A star rotating 716 times per second. I can't even give this video enough frames per second to show you just how fast that is. Anyway, because pulsars, if you stood on the surface of this neutron star, you would be going 70,000 kilometers per second. That's 24% the speed of light. Yeah. So, as I was about to say, because pulsars are very magnetic and compact, their high rotation speeds create beams of electromagnetic radiation, a highly radioactive ray. Speaking of which, gamma ray bursts are a ray of extremely energetic electromagnetic radiation. Gamma ray bursts typically come from either a black hole or a neutron star, like we talked about earlier. If a gamma ray burst were to hit the Earth, it's safe to say the consequences would not be so. We would all die. Quantum mechanics are notoriously hard to understand. Later in this video I will talk about some effects and observations about quantum mechanics, so all you gotta know for now is that quantum mechanics is the science of what goes on in the realm of the super small. We're not talking regular small here, we're talking sizes smaller than atoms. It turns out things get pretty weird once we reach that scale, and quantum mechanics is the science of what goes on in there. The basic principles of quantum mechanics and what makes it weird are a couple of different things. First of all, you cannot describe the location of a particle with certainty. We have a margin of error, and this margin of error is called the uncertainty principle, and has some pretty weird implications. Second of all, particles and their positions are, on the quantum scale, weird to say the least. Particles behave both like a wave and a particle. This is pretty complicated and weird, but the most notorious and, in my opinion, best example of this is the double slit experiment. Let's say we have a screen with two slits. Now, if we point a light to these slits, we will see a wave-like pattern emerge on the other side.
Yeah, but that's not quantum mechanics, that's just light.
Right, have some patience, will you? Anyway, let's do the same, but this time, let's do it with some grains of sand. Each grain of sand would either go through slit 1 or slit 2, and we will see two piles of sand emerge.
Now you're just explaining gravity.
Please just shut the Alright, are you following? Let's say we have a sort of atom gun that can throw individual atoms at a time. If we repeat this experiment, but we block off one of the slits, we can see the atoms spread out like this. So far so good, that's normal, that's fine. Alright, now let's open the other slit again, and what? This is the same interference that we got with light. So basically, the particles move like particles when we have one slit, but move like waves when we have a second slit? Okay. Okay, but how can they move like waves when they're individual particles? Let's try launching one atom at a time, and this time we will put a detector on one of the slits that goes off every time we detect a particle. Alright, yeah, looks like pretty much half of the atoms travel through the upper slit like they should, which means the other slit got the other half of the particles. Now let's have a look at where the atoms— what the fuck? Now the particles move like they should. So when we don't observe them, the particles move like waves, but when we do observe them, they move like particles? Okay. Well, what if we trick the atom and leave the detector there, but this time we turn it off, so they will go through the detector, but we won't actually observe them. I mean, surely they would still behave like a particle and not light unless they were essential. What the Basically, particles move like waves and not like particles, but the moment we start observing them, those bastards start behaving and move like particles like they should. Now, you might be asking yourself,
okay, where's the conclusion? Why does this happen? What's the punchline?
And the truth is, we have absolutely no Some people have, however, come with different theories and interpretations of quantum mechanics. Let's have a look at some of those. So, quantum mechanics are weird and there are a bunch of different interpretations of quantum mechanics. Let's start with the most popular ones. 1. The Copenhagen interpretation. The Copenhagen interpretation essentially states that particles travel like waves until they hit something, in which case they collapse back into the particle. The theory also explains the results of the double slit experiment I explained earlier, since as soon as the particle hits something, like a detector, it collapses from a wave into a particle. The Copenhagen interpretation is the most widely taught explanation to quantum mechanics, but one question remains unanswered. How does it collapse from a wave into a particle? 2. The many worlds interpretation. Unlike the Copenhagen interpretation, the many worlds interpretation says that the particles don't collapse from waves to particles when measured, but instead all possible outcomes of the particle's location happens in different timelines. This is pretty complex, but has some potentially wild implications. These two interpretations are currently the most popular interpretations of quantum mechanics, but there are also some more obscure ones, like hidden variable theories, which state that the quantum entanglement can't be possible. Then we also have cubism, also known under the more boring name quantum Bayesianism. We have quantum Darwinism, transactional interpretation, and a lot more that I won't get into. One of the big difficulties with quantum mechanics has been trying to link the world of quantum mechanics with the rest of physics. If you one day succeed and find a theory that works in both the quantum world and the classical world, we'll have a theory of everything. String theory is an attempt at just that. And here's an introduction. The nucleus of an atom is made of protons and neutrons. Protons and neutrons are made from quarks. But then what? What is the quark made of? Well, string theory proposes that we could see particles not as colorful balls as they're often depicted as, but instead as strings. When we talk about particles, we often talk about them like they're points, but that doesn't really work well with mathematics. But what is more complicated than a zero-dimensional point? A one-dimensional line, a string. And this is where the idea of string theory comes from. Under the theory, particles would be strings vibrating at different frequencies, which determine what particle they are. Unfortunately, string theory requires 10 dimensions to work, and it makes it hard to actually function in practice. But the reason why researchers are still actively trying to make it work is because of how well the math works. If we find a way to make string theory work, it would add gravity to quantum mechanics, something that has been incredibly hard to do, and we could perhaps finally have a theory of everything. I mean, just look at the math. It's it's definitely something. I mean, things in the universe tend to want to achieve a stable ground state. They want to have as little energy as possible. Imagine you have a ball on a hill. The ball's potential energy would be high, and so the ball would not be in a stable position. Pushing would just release its energy easily, but once it has reached a more stable place, pushing the ball would just make it roll back. This tendency for things in the universe to want to reach a ground state is present pretty much everywhere, even for particle fields. Okay, let's go back to the ball example. Let's say the ball hasn't actually achieved the lowest possible state and is instead in a hollow on a slope. If you were to push it just slightly, it would roll back like usual, but if you pushed it harder, it would roll down even further. This phenomenon can happen in the world of particles as well, and is called metastability. Here is where it gets wild. You see, researchers think there's a chance that we are living in a false vacuum. In other words, we live in a state where the quantum fields are not at their lowest point. If one day a particle is pushed into a state with less energy, it could trigger a chain reaction, and the area with the new vacuum state could start inflating. The consequences could be enormous. Some scenarios could still support galaxies, stars, and life, but some scenarios predict that it could mean a complete destruction of all matter, and maybe even cause the universe to implode. But don't worry, it can happen at any time without warning. Moving on. Sometimes, for no reason, there's a random change of energy in a random point in space. This is called quantum fluctuation. Now, you might be saying, well, that disobeys the laws of conservation of energy. Yeah, it actually doesn't. You can pause the video if you want to find out why. Anyway, this essentially results in a particle hopping into existence that is almost immediately cancelled out by its respective antiparticle before we can measure it. This is called a virtual particle. Well, how do we know if they exist then? Well, the Casimir effect supports their existence. One of the big results of these quantum fluctuations is Say you're at your local black hole just vibing, and then all of a sudden a photon appears due to quantum fluctuations.
No big deal, it should disappear immediately before we are able to measure it.
You think to yourself, before realizing that,
Oh no! The antiparticle that was supposed to cancel it out has unfortunately been absorbed by the black hole.
the phenomenon that has just occurred is called Hawking radiation. The amount of energy emitted from the black hole due to Hawking radiation is lower than the amount it absorbs from cosmic radiation, but in a very long time, the black holes will likely start to evaporate completely due to Hawking radiation, and we will likely have what is called the heat death of the universe, where all energy is evenly distributed and nothing can happen. Luckily, supermassive black holes with a mass of 1 galaxy will take 10 to the power of 100 years to completely evaporate. Let's say we knew the position and speed of every single particle in the universe. Could we use this to figure out exactly what has happened in the universe prior to this point? The short answer is yes, since if we know everything about every particle, we would be able to calculate exactly how it got to that point. However, you might say, this assumes that every action that has happened can be calculated back to exactly one state. What if somehow an action had multiple prior states? Couldn't we force two particles onto the same state? Well, as PBS Spacetime's Dr. Matt so wonderfully put it,
quantum mechanics forbids this.
All information about a particle is encoded into its wave function. In other words, information about a particle is guaranteed to be conserved. This is what we say when we say that quantum information cannot be deleted. It is a pretty big part of quantum mechanics. Information is indestructible. Or is it? Calculations suggest this information might somehow disappear and get deleted in a black hole. This phenomenon is known in the scientific community as something that really does not make any sense. According to the cosmological models of today, the movement of galaxy clusters should be distributed randomly in every direction. There is, however, controversial evidence which suggests that the movements of these galaxy clusters is ever so slightly being pulled in a certain direction. This direction is calculated to be outside the observable universe. Digital physics is what we call theories that the universe can be described by information, and that the universe can be seen as the output of a computer program. The implications of this is that everything, all your experiences, the entire world, free will, are but ones and zeros. Calculations done by a computer. Now, this might seem absurd and quite frankly unbelievable to you, but look at it like this. The chances that theory is true might be low, but since we currently have no way of finding out what the truth is, any theory could be correct. I mean, think about it. What was before the Big Bang? What did the universe start? We don't know. Speaking of crazy theories that probably aren't true and that sound completely unbelievable, here's a fun thought experiment. Imagine you're dead. Pretty hard, right? Asking someone to imagine they're dead is like saying, imagine you're not thinking right now. It's not really possible to do so, since imagining a loss of consciousness is not possible. You can imagine not being able to see, hear, smell, or feel anything, but at the end of the day, death is more than just a loss of your senses. It's the loss of your consciousness. If you die, you're not like, looks like I'm dead. So, in a way, you can't really be in a state and reflect upon your death. Okay, imagine you wake up in a room. Next to you is let's say a giant thermonuclear bomb. Okay, you say to yourself, guess I'll just leave this room. But then you look a little closer, find that the thermonuclear bomb is connected to a box, and inside the box is a measuring device that is observing a particle. Once the box is turned on, the spin of the particle is measured, and depending on the spin measured, you have a 50% chance of the bomb going off, instantly killing you, and a 50% chance of the bomb not detonating and being alive. Now wait a minute, you say, I'm Schrodinger's cat right now. Noticing the free opportunity of verifying that quantum immortality is real, you decide to press the button. 3, 2, 1. Pause. You are currently in a superposition of being both dead and alive, and according to the multiverse interpretation, two new timelines are created. One where the bomb detonates and you instantly die, and one where the bomb doesn't detonate and you're alive. Let's unpause. Looks like you're alive. you decide to press the button again. Nothing happened. At this point, there's a 25% chance that you're alive. Okay, could still be lucky, so you decide to press the button 100 times. Okay, so what happened? Well, every time you pressed the button, 2 new timelines were created, one where you were dead and therefore unconscious, and one where you are not. From your perspective, the only possibility for you to exist and so have consciousness is for you to be alive. So for an outsider, the odds of them being alive in the exact same timeline as you are 1 in about this much. But from your own perspective, you cannot be in a timeline where you are dead, because that would mean a loss of consciousness, which, as I described earlier, is not really possible. As a result, according to this theory, you always end up in a timeline where you are alive and therefore conscious. Now, this theory is fairly controversial and has a lot of critique, but it is still a potentially valid theory. With that said, please do not try this out, as there's a good chance this isn't true. Wow, looks like you actually made it to the end of the video. Congratulations, you're probably one of very few. Oh, and if you could maybe press the button that has a symbol of a hand with a thumb pointing upwards, that would be pretty nice. I'm not necessarily talking about the like button, I didn't say that. I mean, I'm not telling you to like this video, that would be cringe and annoying. All I'm saying is that you should look out for buttons with a thumb pointing up, and then, you know, press it if you want. Alright, thanks. Also, I can see from my YouTube statistics that 100% of people watching this are subscribed, so if you can unsubscribe, that would be just fine by me. Alright, thank you so much for watching, and goodbye, I guess. I don't know.